Morning. Uh, Last time we have introduction of high performance concrete. Okay, and today and next time we're gonna look into the details of some of these high performance concrete, including self-consolidating concrete, fiber reinforced concrete, and some other type of concrete. Okay, we also discuss steel reinforced concrete in some details. Okay. So the first one is SCC. Okay. So why we should consolidate the concrete? Okay. The reason is we need to get rid of air voids to ensure good bonding between the reinforcement and the concrete. Okay. And also ensure the concrete will fill every part of the formwork. Okay. And we know for commonly used consolidation method, we can use steel rod. Okay, for small jobs, or we could use internal vibration rod or vibration table for larger work. Okay, like this. If the consolidation is not good, we could have weak or porous concrete. Okay, such as honeycomb. However, too much vibration may not be good. Okay, it may cause segregation and bleeding on top of the concrete. Okay, so that will cause weaker strength of concrete on top first surface, as you can see from here. What is SCC? Okay, SCC is called self-consolidating concrete. It is concrete that can flow under its own weight and without segregation, bleeding. Okay. Okay. Either both during and after placing. For segregation, we could have so-called static segregation, which is settlement of the coarse aggregate to the bottom of concrete after concrete is casted, but still in fresh state. Another type of segregation is called dynamic segregation, which means when the concrete is flowing from one end in the formwork to the other end, during that process, we may have a separation between cement paste and coarse aggregate. We call that dynamic segregation. So that's why we say no segregation during and after placing. So here is the timeline of SCC. The first prototype of SCC is developed in Japan, okay, by Professor Ozawa in 1988. Okay. And the first field application of SCC is in 1990. And 10 years later, SCC spread to the United States. And the first North American conference about SCC is in 2002 in Evanston, Illinois, which is a suburb of Chicago, near Northwestern University. Okay, so that's the time I studied my PhD, which is focused on SCC. Okay. The key property of SCC is focused on fresh properties. Okay, the first one is called flow ability, sometimes also called feeding ability. Okay, which means the concrete can flow into every part in the formwork. Okay, the second one is called passing ability, which means the concrete need to pass around the reinforcement without blockage of coarse aggregate. Okay, this is also very important. Okay, because if we have blockage problems, the coarse aggregate will be blocked by reinforcement, so we have non-homogeneous concrete. The third one is called segregation resistance. Okay, the concrete should not segregate during and after pouring the concrete. Okay, so these three fresh properties is achieved with superplasticizer. We add superplasticizer to enhance the flowability of concrete. Typically, we also use higher cement content. This will increase the cost, but this is important to achieve higher flowability and also higher passing ability. Okay. Sometimes we use viscosity modifier mixtures. These chemical mixtures can enhance the viscosity of concrete, so that will reduce the segregation potential of concrete. Okay. Smaller aggregate is also used. That will reduce segregation potential and also enhance the passing ability. Gradation is also important for SCC. Okay, so we need to optimize the gradation of aggregate. Sometimes we use more than one type of coarse, okay, coarse aggregate. For conventional concrete, we use the slump test. Okay, but for SCC, because it's so flowable, we measure the diameter of the concrete pipe after it stops flowing. All right, so compared to traditional concrete, the good point about SCC is it can reduce the total construction cost. The total material cost will be higher because we need more cement paste. We need more cement. We also need chemical mixtures such as superplasticizer, so that will also increase the cost. But the labor cost will be lower because we have faster construction. We do not need the labor to consolidate the concrete. If you see concrete pouring in the field, you will know consolidation is the most labor-intensive process. Okay, so we save the labor cost. It will also speed up the construction process, so that will also save some cost. So the total construction cost will be lower, even though the material cost is higher. Noise reduction, because we do not need to consolidate the concrete, so noise will be reduced. Performance will be higher because the concrete can flow through the restricted places without segregation. Okay. The strength should be higher because we have more homogeneous concrete. The finish should also be better. Okay. As we can see here, the bottom picture shows SCC compared with conventional concrete. The surface finish is also is better. Okay. The disadvantage of SCC including lack of global accurate testing method and also mixed design method, because relatively speaking, SCC is still new, about 2 or 3 decades. In the US, it is around 20 years, 2 decades. Okay, and also the higher material cost because we use superplasticizer, we use more cement. All right. Again, the 3 fresh state properties: flowability, passability, and segregation resistance. So let's look at how the mixed design parameters will control these 3 performance. Okay. For flowability, it is controlled by how much cement paste is used. Okay. Basically, more cement paste, the concrete become more flowable because it will reduce the frictions between coarse aggregate. We increase the distance between coarse aggregate. Okay. Concrete become more flowable. The viscosity and yield stress of cement paste, we call that paste rheology, is also important. Okay, that is controlled by water to cement ratio, admixtures. Okay. And also the packing density of aggregate. Okay. How well we pack the different type of aggregate can also somehow control the flowability of concrete. The test method for flowability is the slump flow test, as we saw earlier. For passing ability, again, passing ability defined as how well the concrete can pass through the reinforcement without blockage of coarse aggregate. The controlling factor including the maximum size of coarse. Okay, the larger the coarse aggregate, the easier for the aggregate to be blockade behind the reinforcement. Increased volume of aggregate will also reduce the passing ability. Better gradation will reduce the likelihood for blockage, so increase the passing ability. The test method including airbox test and also J-ring test, which will be discussed in a moment. Right. For segregation resistance, the controlling factor including water to cement ratio. If we reduce the water cement ratio, that will increase the viscosity of cement paste. Okay, so the segregation resistance will be higher. If we use more sand, that will also reduce the potential for segregation. Or we use VNA, that will increase the viscosity of the paste, so reduce the segregation resistance. Okay. The testing method including HVSI, which is Harden Visual Stability Index. This is one of the standard method developed here at UH. And also column segregation test, which will be discussed in a moment. Okay, so let's look at the slump flow test. Okay, this is the standard test, ESTM test. Okay, so it is very similar to the slump test for traditional concrete, but we pour the concrete with 1 lift instead of 3 lift. Okay. Without any consolidation. Okay, no 25 strokes for each layers. So after pouring, we just leave the cone and we let the concrete flow under its own weight. So we record the time it takes the concrete to reach a certain diameter, which is 50 centimeter, 20 inch in diameter. So the commonly accepted value is less than 12 seconds. Okay, more than that, the concrete becomes too viscous. We also measure the diameter. Okay. For normal SCC, it is around, I will see more than 22 inch, less than 30 inch. Okay. If the slump flow diameter is too high, the concrete tends to segregate. And we can also observe the segregation, which is by say the parameters of the concrete pipe. Okay. If we see a layer of paste around the parameter, then the concrete will definitely be segregated. Okay. However, sometimes the concrete will not segregate at a parameter, but in real situation, it still may segregate. Okay, we're going to talk about that in a moment. So here's a video for the slump flow test. Okay, the cone is actually upside down. Okay, the smaller diameter is in the bottom. All right, so we fill the cone with 1 lift, no consolidation. And then we lift it. We measure the time for the concrete to reach 20 inch in diameter. And we measure the final diameter. All right, airbox test is another test to check the flow ability as well as passing ability. Okay, so this is the instrument. Okay, we have 2 sections, the vertical sections and also the horizontal sections. And if you can see here, we have a gate separate the vertical and horizontal sections. We also have some rebars here. Okay. So first of all, we close the gate. We fill the concrete only on in the vertical direction, vertical section. Okay. And then we leave the gate and we let concrete to flow to the horizontal sections. The concrete will also pass through the reinforcement. And then we measure the height at the 2 ends of the horizontal leg. Okay, so and we get a reach of these two heights. Okay, so more than 80%, this thing is okay. Okay. Here's a video for the airbox test. Okay, again, we have a gate here before we pour the concrete. We also have some rebar. Okay. We pour the concrete. And we leave the gate and measure the time for the concrete to reach the other end. And then after concrete stops flowing, we measure the height at the two ends. Okay. This is another view. As you can see, the concrete pass around the reinforcement. Okay. That's why airbox test check the passing ability. Yeah, good SCC can easily pass around the reinforcement without blockage of coarse air gate. Okay. So that is the airbox test. The gearing test is also measurement of passing ability. Okay, actually we put a ring. As we can see, we have some rebar with certain spacing. We have the slump flow cone here. Okay, we measure the slump flow, but with the ring. Okay, and because we have a ring here, the diameter will be smaller if we have a passing ability issues. So we compare the diameter of the concrete with the ring and without the ring. Okay, so that's the indication of passing ability. So that is the gearing test. This test is a measurement for static segregation, okay, which we call that column segregation test. This is another ASTM standard test. Okay. The column, I believe, is around 10-inch and maybe 24-inch in height. And we have top, middle, and bottom sections. And we have separation, okay, between these three sections. Okay. Initially, we pour the concrete in one lift and fill all the three sections of the concrete. Okay. And we let the concrete to settle for around 15 minutes. Okay. If the concrete has segregation problems, in the bottom section, we should have more cross air gate. Okay, and then we just take the top sections, take all the concrete, and also take all the concrete at bottom sections. And then we wash out all the concrete, we wash out all the cement paste, only cross air gate is left here. And then we can measure how much cross air gate is in the top portion and how much cross air gate is in the bottom portion. And we compare the difference between the weight of cross air gate. Okay, too much difference, we see the concrete has segregation problems. Okay, this test is time consuming and use a lot of materials, and because we need a lot of water to wash the concrete. Okay, it is not a very field-friendly testing method. So that's the reason we try to develop some other test method, like the so-called segregation probe method. Okay. So this method is developed here. Actually, when I was a PhD student at University of Illinois, we start developing this method, and then we finalize the design here at UH Manoa. Okay. So this is the simple probe made by a steel wire. Okay. The total weight of the steel wire is around 28 grams, I remember. Okay. It's a certain size. Okay. What we do is we cast the concrete into a 6-inch by 12-inch cylinder. This is fresh concrete. And we gently put the segregation probe on top of the concrete. Okay. So the probe is designed that it will penetrate the cement paste or mortar layer. but it cannot penetrate when the concrete has coarse aggregate. Okay. So this is designed based on fluid mechanics. Okay. So the yield stress of the suspension, either mortar or concrete, should be larger than 30 Pascal to prevent the settling of a segregation probe. Because for mortar, the yield stress is less than 15 Pascal for SCC. And the yield stress for concrete is more than 50 Pascal. So that means the probe will only penetrate the paste or mortar layer, but cannot penetrate the coarse aggregate. Okay. So we use the probe to easily measure the layers of mortar on top of the concrete. And depending on the penetration depth, we can give a 0 or 1, which means the concrete is stable, or 2 and 3, which means concrete is not stable enough. Okay. Based on the segregation probe, we also developed another testing method for hardened cylinder, hardened concrete. Okay. So we let the concrete to set, harden, and we cut the concrete in half. And based on the observation of the distribution of coarse aggregate along a layer, okay, for example, reaching 0, stable means there's no mortar layer at top of the plane and no variation in size and percentage of coarse aggregate. Okay. Stage 2 means we have slight mortar layer, less than 1 inch in thickness. Okay. And we have distinct variance in the size and percentage areas of coarse aggregate distribution from top to bottom. Okay. So based on this criteria, we can also give a stability reading from 0 to 1, which is stable. Okay. When the concrete is rated as stable, that means the concrete will not crack. This is based on finite element simulation. Okay. But if the concrete is not stable, we may have some cracking due to shrinkage. Because remember, only cement paste will shrink. If we have only paste layer on top of the concrete, and because again, only paste will shrink, and also the water cement ratio on top of concrete is higher because we may have some bleeding issues. So the top layer may be cracking due to segregation issues. Okay, right now this standard is national standard, is AASHTO PP58. Okay, we call that static segregation of hardened sep consolidation concrete. All right, then let's look at some research on SCC. Okay, just some example. Okay. So in this research, we compare different concrete mix. So S35, F0 means the concrete has water cement ratio of 0.35. Okay. F0 means we have 0% of flash. F20 means we have 20% of flash. Okay. And here means we have water cement ratio of 0.45 and the flash percentage of 0, 20%, and 30%. Okay. So what we can see is if we increase the percentage of flash, we need less amount of superplasticizer to achieve the same durability. Okay, that means we save the money for superplasticizer. Okay, and also at higher water to cement ratio, the effect of superplasticizer is less sensitive compared to concrete with lower water to cement ratio. Okay, this is just an example. Here shows the same 6 mix, but showing us the strength at 1 day, which is blue. The red is 7 days, and the yellow is 28 days. Right. So what we can see is for the same 0.35 water cement ratio, if we increase the percentage of flash, the strength at 28 days and also 7 and 1 days will be lower. So the reason for that is because, remember, flash is pozzolanic materials, okay, and pozzolanic reaction is slower. Okay. And same thing for 0.45 water cement ratio. And here shows same 6 mixes, but the permeability result. Okay. So here shows the results. The blue is permeability at 2 weeks. The red is 16 weeks, almost 4 months. And we can see the effect of flash. Okay. A great reduction in permeability at 16 weeks, not so much at 2 weeks. Again, this is because pozzolanic reaction is slower, but in the end, it will reduce the permeability quite a lot. Okay, so the beneficial effect of flash occurs at later age. So if we use flash or slag, we want longer curing to ensure the pozzolanic reaction will keep going for months. All right, so that's the introduction of SCC. Next, let's look at the steel reinforced concrete, basically the steel rebar. Okay. So compared with concrete, steel has much higher strength and much more ductile. It is 10 times stronger compared with traditional concrete under compression, and in tension it is 100 times stronger. Okay. The tensile strength and the compressive strength of steel is almost the same. For concrete, concrete is much stronger under compression compared with tension. The best thing about steel is, first of all, it is much more expensive. And it's not very durable. The resistance to fire, high temperature, and corrosion is not very good. That's why for reinforced concrete, we need to, for steel members, we need fireproofing, and also we need to ensure the corrosion resistance of steel member is good enough. Okay. And because of this, we need to combine the steel and the concrete together. We use steel in tension zone of beams and slab, and also when the reinforced concrete member will experience shear, because again, steel is strong under tension and shear. Concrete, not so much. Under compression, we can also put rebars, that it will reduce the cross-section size, okay, of the beam. Right. For steel reinforced concrete, we need to ensure the steel bar will work together with concrete under the load. Okay, so that means a good bonding is very important. That's the reason why most of the case we need a deformed surface, as we can see from here. So that will provide mechanical bonding between the rebar and surrounding concrete. The rebar has different size from number 2 to number 18. So the nominal diameter is around the bar number times 1/8 inch. For example, number 8 rebar has nominal diameter of 3 times 1/8 is 3 inch. Okay. Right. So most of the rebar will be deformed rebar with rough surface. But sometimes in special situation, we may also use plain rebar. That is in a situation where we do not want good bonding between the rebar and the concrete. For example, for highway pavement, we may put the rebar across the expansion joint, okay, but we do not want a strong bonding between the rebar and the concrete. because otherwise the concrete may crack due to the tensile stress, and the rebar will restrain the concrete from expansion and shrinkage. So we put plain surface rebar. So the rebar will provide the resistance so to prevent the concrete from settlement differently. Okay. So this is a special situation. But for most of the case, we want deformed rebar to ensure a good bonding between rebar and concrete. Right. So let's look at the chemical component of reinforcement, steel reinforcement. We have basically two components. Ferrite, which is pure iron. So pure iron has lower strength, but more ductile compared to the other component, which is cementite. Okay. Cementite is also called iron carbide. It's Fe3 with carbonate. Okay. So we increase carbon content in reinforcement, we increase the percentage of cementite. So the strength of the rebar will be higher, but it will reduce the ductility. Okay. So we combine the percentage of these two components. Okay. So we can alter the mechanical property of the steel. Okay. More cementite, we have higher strength, but the steel will be less ductile. So we increase the carbon content, we increase the amount of cementite. Okay, so strength will be higher, it will also be harder, okay, but that will reduce ductility. But the modulus of elasticity will not change as much by increase or reducing the carbon content. Okay, so here is the important notes. For steel structure, for structure steel, it has limitation on the carbon content, no more than 0.3%. So that will ensure the rebar will be ductile enough, so the steel reinforced concrete member will not have a sudden failure. Okay, so that is important for short safety. No sudden failure, and limit amount of carbon content to 0.3% or less. Okay. So we have different grade of steel rebars, from grade 40 to grade 90. So grade 40 rebar has yield point of 40 KSI, okay, and grade 90 has yield point of 90 KSI. What we can see here is the slope of this stress and strain curve for all grades of steel rebar is almost the same. That means the modulus of elasticity is almost the same, even though the stress level are different, the gradient is different. Okay. For pre-stressing steel, this E value will be a little bit less because we want to reduce the potential for creep and relaxation in pre-stressing concrete. But for all other rebar, the E value will be constant, around 29,000 KSI. And here shows why we need to put the reinforcement in the beam. Okay, so here shows the plain beam. Okay, so without rebar, the concrete will crack early in the tension zone. Okay, so the moment resistance of this plain beam will be much lower. Okay, if we put the rebar in the tension zone, the rebar will take most of the load under tension. So the moment couple will be much higher when we put the rebar compared to the plain beam. Okay. For steel to work, the concrete must crack first because concrete is very brittle. Under tension, it will crack very early. But just a little bit crack will make sure the rebar will take most of the tension. Okay. Again, steel is placed in tension zone, and the steel is closed most of the time except for these minor cracks. Okay. The concrete is very important to protect the steel from corrosion. As we discussed in the lectures of durability, the alkaline environment of concrete will protect the steel from further corrosion. Okay. So that is reinforced concrete. And that's it for today. Next lecture, we will talk about fiber reinforced concrete and other type of high performance concrete.